There are some basic graphs which will make our life easier if we define it and give name. So for a graph G, which consists of the vertex set P and edge set E, we write G bar to denote the graph, which consists of the same vertex set, but the complement of edge set. So here, this V choose 2 is the all UV where U and V are in V. So we write this as a set of all pairs inside of this set. Then, what does this graph mean? So edge set is actually flipped. All the pairs, adjacent pair become non-adjacent, and non-adjacent pair becomes adjacent. So UV is on H in G, if and only if. I write IFF to denote if and only if. UV is non-H in G. And we denote that as a graph isomorphism graph, as an unlabeled graph, the graph with n vertices and all possible and choose 2 edges is denoted by K sub n. Capital K with the subscript n, and this is called a complete graph. This is complete graph on n vertices. And the empty graph on n vertices is complement of this complete graph, which is the graph with no edges. And 0 edges, and which is denoted by complement of K. And we call this as an empty graph. And we give a name of a subgraph of certain graph, which looks like complete graph or empty graph. And we said a click in G is a subgraph which is complete subgraph of G, and an independent set, or sometimes it's called a table set. In G is an empty induced subgraph of G. In other words, clique is a collection of vertices where all the pairs are adjacent, and independent set is a collection of vertices where all the pairs are not adjacent. And we write alpha of G to denote the maximum size of an independent set of G. And we call that the independence number. And we write omega of G to denote the maximum size of a clique in G, called the clique number of G. Okay, so these are also useful concepts. And another useful concept is we say that a graph G is R-partite. If this is the union of R independent sets. Especially if R equal 2, we say that G is a bipartite graph. And this bipartite graph is important. For example, in the previous example, if there are jobs, then like applicant, the candidate, then we were adding edges if this candidate is capable of doing this job. There, we have this bipartite structure because jobs cannot be capable of doing other jobs, and candidate is not capable of doing other candidate. It's strictly between jobs and candidate, and those two are disjoint. And this special structure give you further things that you can do when you are solving problems. So it's useful concept, being bipartite, or in generally being R-partite. So all the edges are between these two sets, which is same as this upper set is independent and this lower set is independent. We say that X and Y is a bipartition of G, or we say that G is an XY bipartite graph or bigraph if this is a partition of the vertex set of G into two independent sets. So oftentimes I just write in this to indicate independence. And another definition, another useful concept is graph being regular. We say that the graph is regular if all vertices have the same degree. And we say that it is k-regular if that degree is k. And we also write the big delta of G to denote the maximum degree of out of all the vertices. And small delta of G to denote the minimum degree. And yeah, maybe we prove one simple statement regarding the degrees, which will be useful later to prove other things, we can ask a simple question. Is there three regular graph on 7 vertices? In other words, I mean, we can imagine like 7 people, and then they shake hands. Whenever they shake hands, we add an edge. Can we end the situation where everyone is shaked hands with exactly 3 other people? And the following lemma, which we call a handshake lemma, this handshake lemma says that this is impossible. What does it say? Every graph contains even number of vertices with odd degree. Then 7 vertices with odd degree. Here 3 is odd number, it's impossible. And how do we prove this? We consider the summation of all the degrees of the vertices in G. Maybe I'll just write B here. Then what do we get? So you have this graph. From this vertex, you count this edges. From this vertex, you count this edges. And from this, you count these edges. And from this vertex, you count these edges. And finally, from this vertex, you count these edges. And what happened? Every time from a vertex point of view, you count the edges incident with it. But if you flip the situation and see from the edges point of view, this edge is counted by this vertex and then by this vertex. It has 2 endpoints, and then in counting edges from each endpoint is counted. So in this expression, every edge is counted twice. So this sum is an even number. So that says that its sum is even. That means the number of odd numbers here, which is added, must be even. So I will not write down the further sentences to finish the proof. So this is called the degree sum formula. And it will be helpful later. And yeah, finally, let's define one more concept of directed graph. So as before, we have certain problem. We lose the or redundant information, and we just keep the essential information. That was the motivation for defining this graph. And in some cases, there are additional information that's also required to be kept. For example, in the roadmap, some of the maps are one way. From here to here, there is a way to get there, but not the other way around. I mean, that's totally, I mean, we often encounter that on the road when we are driving, for example. So in order to deal with certain problems, we want to keep the orientation of the edges. So we give the definition of this more general concept, this directed graph. Or we simply say digraph. If D is an again ordered pair, BE, where this E is subset of B dot B, B cross B. So before UV and BU were same in the graph, in undirected graph. But here, U comma V is different from B comma U. So this U comma V, you think as from U to V. Then these two are different. So this is what we call digraph. And we say on edge or directed edge or on arc, sometimes we call it an arc, E UV, or you write U to B with the arrow on top. This is from U to V. And we say that U is it's either tail or source, and B is its head or sink. I mean, you consider it as a arrow, and then it's tail and head. You consider it as a flow of something, then it's source and sink. And we say that a digraph is an oriented graph if it can be obtained from a simple graph by giving orientation on its edge. Meaning that if UV is in here, then VU is not in here. So what it means by if you have a simple graph and you give an orientation, meaning that you have only one edge between them. So giving this orientation forbids this. Also, this forbids a loop. So in directed graph, there could be a loop B to B. But this says that if BB is there, then BB should be not there, which doesn't make sense. So in the oriented graph, you have a no loop. So it's indeed coming from a simple graph by giving the orientation. That's exactly coincide. It's the equivalent definition. And we say the underlying graph of an oriented graph is the one that's obtained by making the edges unoriented. So you have a oriented graph, and then you forget the orientation on each edge. Then you get the simple graph, which is called the underlying graph. And we say that on orientation of a graph G is an oriented graph with the underlying graph G. And especially if you have a complete graph and orientation of a complete graph, we give a name of tournament. So a tournament is an orientation of a complete graph. This name comes from the following interpretation of the diagram. You draw this U to B, then you can interpret as there was a game between U and B, sports game, let's say tennis. And then if U beats B in this game, you draw this. Then what's a tournament? It's there are players, and then every pair of them plays a game, and then determine who wins on that game. that give you an orientation of a complete graph. So the name tournament come from that. And finally, if we have a directed graph, then we define its out degree and in degree. And that's the number of, so when I write down this sharp, then this means the number of edges from B, and it's called the out degree. And this is number of edges to B and called the in degree. Okay, so let's give some definitions that we need. And in next video, we define, further concept, which is useful and necessary to talk about the connectivity of the graph. And then we will prove some basic facts about the connectivity. Which prove some basic facts about the relationship between those concepts, which will help us to understand the connectivity of the graph. Okay, okay, thank you for listening. I will see you in the next video.